Can you hear me properly? Okay. So we'll start from the question. A person of mass 60 kg, a person of mass 60 kg is inside a lift, is inside a lift of mass 94 kg, okay, of mass 940 kg and presses button on control panel, okay, and presses button on control panel. The lift starts moving upward with the lift starts moving upward with an acceleration of 1 meter per second square, okay, or with 1 meter per second square, okay. So from unit you can identify this is acceleration, okay. So if acceleration due to gravity, if g is equal to 10 meter per second square, then the tension in supporting cable is, then the tension in supporting cable is how much? Okay. So the mass of this person is 60 kg and he's sitting inside the lift of 940 kg. And okay, so let's say this is the top, there is a cable and lift is there and this person is standing in the lift. So mass of this person is 60 kg. Mass of the lift is 940 kg. Okay. And it is moving upward with acceleration of 1 meter per second square. So if we draw the FBD of this, let's consider this mass man as well as this lift as a single unit. If you consider this as a single unit, then the total net mass is 1000 kg. So 1000 into acceleration due to gravity. So it is like 10,000 Newton force is acting in downward direction. Then there is acceleration 1 meter per second square and lift is going upward and see there will be tension in this string. So let's say T is the tension in this string. So since lift is going upward, let's consider forces in upward direction as positive and forces in downward direction as negative. So what we will get basically, if we solve F equal to ma, then F is basically T minus 10,000 is equal to ma. Here m is 1000 kg and a is 1. So basically you get tension is equal to 1100 Newton. Okay. Let's go to the next question. A mass of lift is 2000 kg. Have you understood? Okay. So a mass of lift is 2000 kg. A mass of lift is 2000 kg when tension in cable is 28,000 Newton. Then it is accelerated at, okay. So you have to find the acceleration of a lift, and they have given the tension in the cable. Okay. So let's say, so I think you was not there when we have learned about like if what is the tension if lift is going in upward direction and how much is the tension when it is going in downward direction. So let's say we have a cable and lift is connected to the cable. Okay, we'll consider two cases. Okay, so in let's say in first case lift is moving in upward direction. In second case lift is moving in downward direction. So let's say T is tension in both the cases, and lift is accelerating upward with acceleration, let's say A, and here also it is accelerating downward with acceleration A, and there is some mass of lift, so force mg is acting downwards. It is basically mass of lift or mass of lift per plus person it is carrying, so it is, let's say, mg. So if you see the first case, since lift is moving upward, let's consider forces in upward direction positive, so T is positive, the net force is T minus mg, and it is equal to ma. So you get tension in the lift string or cable is basically ma plus mg. In second case where lift is moving downward, here since lift is moving downward, forces in negative downward direction is positive. So let's say mg minus t is equal to ma. So here you get t is equal to mg minus ma. Okay. So you can see from both the cases. So when lift is going upward, tension is ma plus mg. So it is mo so the tension in the string will be greater than tension in the string will be greater than mg when lift is going upward, whereas when lift is going downward it will be lesser than mg. Okay, so now if you see this case, a mass of lift is 2000 kg and g is basically 10 meter per second square, so mg will become 2000 into 10, so that is 20,000 Newton. So the weight of the lift is 20,000 Newton. Tension in the cable is 28,000 Newton. It tells us that lift is moving in upward direction. So because then only the tension will be higher than the weight. So when lift is moving in upward direction, we know that T is equal to ma plus mg. So here T is 28,000. Ma is unknown, but what they have given is mass of the lift. So let's say 2000 into acceleration A plus mg is 20,000 we have. So from this we get A is equal to basically 4 meter per second square if you solve this. Okay, you got this? Okay, let's move to the next question. A man weighs, or let's say man with mass 80 kg. Okay, he stands on weighing scale in a lift. He stands on a weighing scale in a lift which is moving upward with uniform acceleration. 5 meters per second square. Okay, so what would be the reading on scale? So, what would be the reading on a scale? Okay, so a man with weight 80 kg, he stands on a weighing scale in a lift which is moving upward with acceleration 5 meter per second square. Okay, so let's say again you have this arrangement. So there is a lift. Okay, and let's say this is a man. He he weighs or his mass is 80 kg. Okay, and lift is moving with acceleration 5 meter per second square. So basically lift is moving and therefore this man is also moving with acceleration 5 meter per second square, and he is standing on a weighing machine. So whatever reading that weighing machine will show is basically the normal reaction of this man. Okay, so whatever will be the normal reaction of this man, that is equal to basically this reading on the weighing machine. So now if we draw the FBD of this man, let's say n is the normal reaction, which is the reading on the uh, weighing scale. Okay, so this is n is the normal reaction provided, and he's moving with acceleration 5 meter per second square, and it's his weight basically mg, that is 80 into g is let's say 10, so g is 10 meter per second square. So 800 in 80 into 10 is 800 newton. His weight is acting in downward direction. So since he's moving in upward direction, let's say n minus 800 is equal to ma. So m is again 80 into pi is the acceleration. So it will be equal to 400 plus 800, and it will become 120 Newton. So basically normal reaction provided will be equal to 120 Newton. Sorry, 1200 Newton. 1200 Newton. Understood? Okay. Next question. A monkey of mass 20 kg. So one more thing I just wanted to tell you here in this problem. Okay. So if there is concept of pseudo force. Okay. So concept of pseudo force basically tells us that, like, okay. uh, what- So now this person lift was moving with, this person was standing in lift, and lift was moving with acceleration a. Okay. So if we see from outside, we know that this man is moving with acceleration a, and therefore when we have drawn is FBD, we have uh, what? Then therefore we have seen basically that we have considered his acceleration. Okay. Whereas if this man is sitting, again lift is moving upward, this man is standing. Okay. And if someone sitting here is seeing this person, then according to this person, let's say this is person A, according to B, A is not moving basically, because he will see. So this, first, whatever we see with stationary like frame of reference, where we are seeing whole lift and man is moving, this is inertial frame of reference. Frame of reference. And when this person sees this man A, when B sees A, he will see he is not moving. So he sees A in non-inertial frame of reference. Okay. Frame of reference. So if you now try to draw the FBD by considering the reference of person B, then basically he will say that there is weighing machine. This person is standing. Okay. And since his weight is acting like mg downwards, so normal force is also equal to mg, and therefore he will, according to him, the n or weight should be equal to mg only in on weighing machine. But since he is not moving, or he is moving with same acceleration to that of person A, in this case we will apply pseudo force F on this person, and the which will basically match this mass into acceleration. So that pseudo force will be equal to mass of this person into acceleration of this person. And therefore, this normal reaction N, now it will become mg plus pseudo force F, and where that F is equal to ma, mass of this person into acceleration of this person. So therefore, we will get normal reaction as mg plus ma. So this is only when we introduce the concept of pseudo force only when we are solving the problem using non-inertial frame of reference. Okay. And non-inertial frame of reference means the person which is observing the motion is also moving with same acceleration, or with that uh, the object of our interest. So basically it simplifies the question, or it do same thing only, like there is no any different, only the frame of reference changes, and therefore when frame of reference changes and that person is also moving with same acceleration with our object, then we basically apply the force which is required to bring our object at rest. So that will be equal to F equal to ma in opposite direction to the direction of its motion. So this is how we solve this question, this kind of question. So it is, means you can solve it using pseudo force concept, or you can directly solve our using our mm, conventional methods. Okay. Where you consider the motion with respect to ground or stationary things. Okay. So moving to the next question. A monkey of mass 20 kg is holding a vertical rope. you got that pseudo force concept, or you want me to tell you once again? Okay. A monkey of mass 20 kg is holding a vertical rope. The rope will not break when a mass of 25 kg is suspended from it. A rope will not break when a mass of 25 kg is suspended from it, but will break if the mass exceeds 25 kg. What is the maximum acceleration with which the monkey can climb up the rope? Here g is given as 10 meter per second square, and options are: A is 5 meter per second square, B is 10 meter per second square, C is 25 meter per second square, and D is 2.5 meter per second square. So they are telling us like monkey is having mass 20 kg, and a rope will not break when mass of 25 kg is suspended. But if mass is above 25 kg is suspended, it will break. So let's say this is the rope, okay? So if you suspend 25 kg, then it will not break. But if you cross 25 kg, then it will break. So when you suspend 25 kg, the tension in the string will be 25 into gmg. It will be equal to 250 Newton. So basically, when tension in the string crosses 250 Newton, it will break. Okay. So it should not cross 250 Newton. Now there is a monkey which is climbing up. It is having mass of 20 kg. It is going up with some acceleration. Let's say now T is the tension in the string. So now if you draw the FBD, so it will be downwards 20 into 10, that is 200 Newton, that is weight of the monkey. Let's say A is the acceleration, since he's climbing up, we will show it is in upward direction. And let's say T. So since he's climbing up, T is positive and 200 Newton is negative because T is in direction of acceleration. So T minus 200 is MA. So M here is T minus 200 is equal to M is basically 20 kg into A is unknown. Okay, 20A. So we got T into 200 is equal to 20A. When he is climbing up, this equation holds basically. So now if what is the maximum acceleration with which he can climb, so rope won't break. So if tension in the string goes about 250, it will break. So maximum tension it can withstand is 250. So 250 minus 200 is equal to 20A. So A is become 50 by 20, that is 2.5 meter per second square. Clear? Now I will give you one question, okay? I will give you 2 minutes to solve this. A mass of 1 kg is suspended by thread if, okay, so it is, first is lifted up with an acceleration 4.9 meter per second square, lowered with, or okay, lowered with an acceleration 4.9 meter per second square, and g is given as 9.8 meter per second square. So let's say the tension in the string when it was lifted up was equal to T1, okay, and tension in the string when it was moving down, we were lowering it up, then it was T2. So find T1 upon T2. Okay, okay, fine. So you have 2 minutes to solve this. Please give an attempt. Okay, you got the answer as 3. Okay, fine. So there are two cases. In first case, uh, it is moving upward, and in second case, it is moving downward. So let's say this is 1 kg, this is T1, and it is moving upward with acceleration 4.9 meter per second square. And in second case, it is T2, it is 1 kg, and it is moving downward with 4.9 meter per second square. So of course, in this case, T is ma plus mg. So ma is 1 into 9.8. Sorry, mg is 1 into 9 plus 1 into 4.9. That is T is equal to, or basically T1 is equal to 13 and 1.7. So 14.7. And in this case, T2 is basically equal to mg minus ma. So 1 into 9.8 minus 1 into 4.9. So T2 is 4.9. So T1 by T2 is 14.7 by 4.9, and it is equal to 3. Correct. Okay, 3 is the correct answer. So now we will move towards spring. So earlier we have seen example with cable or cord. So let's say we have seen, let's say this is mass m. Then there is a second cable or cord with mass 5m, and again we have third one with mass 4m. So we know that we what we used to do is, we, since every cord or every cable tension will be different. It will be, let's say T1, it will be T2, it will be T3, and we used to draw FBD. So if we draw FBD for this 4m mass, then you can find out the tension in this string. T3 is basically 4 mg. Similarly, T2 will be equal to 9 mg, and T1 will be equal to 10 mg. Okay, you basically we will have to draw the FBD only. And similar similarly, now if you have a spring, let's say, so in spring also tension will be similar. So in this uh, case, it will be 4 mg, it will be, here it will be 9 mg, and here it will be 10 mg. Okay, so if you have a let's say spring of length L. Okay, if you have a spring of length L, now if you apply force in both the directions, so its length will change. Okay, if you apply force in both direction, its length will change. Okay, let's say you have applied force F. So now it has like its length has increased. So let's say this was its earlier length L, and now its length is basically L plus X. X is basically change in length. And in similar manner, if you compress this spring, its length will decrease. So again, let's say you are applying force F to compress the spring. So L was the initial length and X is the change in length. Okay. So here L is initial length and X is change in length. So one thing you have to understand is like if you are applying force F and its length has increased to L plus X. So in this case, there will be restoring force of equal magnitude F that will start acting in opposite direction, and so that it will like this is basically kind of a restoration force, and this force will want that lift that spring to go in its initial position. Okay, so when you have you have pulled the spring from both the sides, there is restoration force F will act in opposite direction. Okay, similar manner, if you compress the spring, there will be, let's say if you compress the spring with force F, then there will be restoration force F which will try to bring this spring in its original position. Okay, there will be some restoration force. So from there, uh, basically the Hook, he was the scientist and he gave a law that this restoration force F is directly proportional to change in length, or F is directly proportional to minus X. And this minus sign is because this restoration force acts opposite to the direction of change in length. Okay, so like if you see this case, let's say you have attached a spring here. Okay, one second. Okay, so it became, I will tell you, finally it became F equal to minus kx. So this is Hooke's law. Or you can consider F equal to minus kx, or this F is restoring force here. Okay, so restoring force is basically acting opposite to the force you have applied. So in general, whenever you will use the equation F equal to kx, because we will generally consider the applied force. So let's say you have a spring, you have applied force F. Okay, let's say initially it is at this position. Forgot this. Initially this spring here ends here. Now you have applied force F. So let's say this was the length of the spring L, and now it became this much. Okay, and this is L, this is X is change in length. So you can see that when you are applying force in this direction, restoring force will act in opposite direction. So change in length is also in this direction, and restoring force is acting in opposite direction. Therefore, this F is directly proportional to minus X equation came. Okay. However, if you see our force which we have applied, it is in same direction as of the change in length, and therefore generally we will use this equation F is equal to kx. For compression also, you can see if you apply compressing force F, of course, the length of the spring will change. And in this case, change in length is in this direction. Our applied force is also in same direction. So we can directly use F equal to kx in this manner. Okay. So here k is basically spring constant. Spring constant. And this spring constant, you know, F equal to kx. F has unit of Newton, k has unit of meter. So sorry, x has unit of meter. So k has unit Newton per meter. And it this is unit of spring constant. Okay. And this spring constant depends on stiffness of spring. Sorry, stiffness of spring. Okay. This spring constant depend on stiffness of a spring. So let's say now you have a spring with stiffness 1000 Newton per meter, and you have applied force of, let's say, 100 Newton on the spring. So what will be the change in length of a spring? Okay, change in length of a spring. So we know that F is equal to kx. Here k is sorry, F is 100, k is 1000, and into x. So x will become 0.1 meter. This is the change in length. However, if here in this case k was 1000, okay. Now if you take k as 100 only, 100 Newton per meter. So in this case, F is 100, k is 100, and x. So you will get x as 1 meter. So if k is large, x is small. Basically, they are inversely proportional to each other. Okay. Any doubt till this point? Okay. So now let's say we have a question. We have a spring with K spring constant of 5 Newton per meter, and mass of the object which is attached to the spring is, let's say, 8 kg. So find out this change in length of the spring. Okay, change in length of a spring. So if mass is 8 kg, so of course, if g is 10 meter per second square, so force will, like, weight will act 8 into 10, that is 80 Newton force will act on the spring. So we know that F equal to kx. So 80 will become 5 into x. So x will be equal to 16 meters. So this is how you can solve this question, this kind of question. Now we will see what will happen to the spring constant if we arrange the spring in some manner. Okay. Basically, we will see combination of a or of springs. Now let's say you have three springs connected in series. Okay, and stiffness of these strings, let's say this is K1, this is K2, this is K3. So the net, if you have to find K effective or K net, so effective spring constant in this case, K effective will be given as 1 upon K1 plus 1 upon K2 plus 1 upon K3. So you should remember this formula. So this will be their effective spring constant. So now let's say we have a question. So we have three s- springs connected in series. So where the spring constants for all springs are given. So you have to find out the effective spring constant. So effective spring constant, we know that it can be given as K effective is 1 upon K1 plus 1 upon K2 plus 1 upon K3. So it will become 1 upon 2 plus 1 upon 10 plus 1 upon 20. So we'll try to make the denominator same. So we'll multiply the first term with 10. So 10 upon 20. We'll multiply second term with 2. So 2 upon 20. And we'll keep third term as it is. So 3 upon 20. So finally we will get 13 upon 20. So K effective will be, since 1 upon K effective is 13 upon 20, K effective will become 20 upon 30 Newton per meter. Okay. So similarly, if you have three springs connected in series, then two spring connected in series, then if K effective will become 1 upon K1 plus 1 upon K2. Or if, let's say you have n springs connected in series, then K effective will be 1 upon K1 plus 1 upon K2 plus dot plus 1 upon K spring constant of nth spring. So this will be the formula. Okay. Got it? Okay. Yeah, I will tell. Okay. Okay. So this was about springs in series. Now, if we have springs connect in parallel, okay. So let's say this is a wall, and there are two springs. Let's say this is having K Newton per meter spring constant. This has K2 Newton per meter. First one is K1, second is K2, and it is connected to an object, let's say, of mass m. So in this case, K effective is given as K1 plus K2. It is, when it is parallel, it is simple addition. So let's say if you have three springs connected like this, to some object of mass m kg. Let's say it is having K1, this is having K2, so it is having K3. So K effective will be K1 plus K2 plus K3. Okay. So in this similar manner, if you have n number of springs, n springs connected in parallel. So K effective will be K1 plus K2 plus dot 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 addition K3, K4, K5 similarly to K of nth spring. Okay. So there is one more case. Okay. So if you have a object of let's say mass some mass mkg is connected with two spring like this to a wall. This is let's say K1, this is K2. Then it is considered as springs are in parallel, and therefore in this case also K effective will be K1 plus K2. Okay, so you should not get confused with this kind of question. So in this case also, net or effective spring constant is considered as that of parallel case, and it is therefore K effective is K1 plus K2. Can you find out the change in length of the spring in this case? Okay, just find out change in length of the spring in this case. I will wait for 1 minute.
Sorry, you're muted.
Okay. So K effective is basically 1 upon 5 plus 1 upon 5 is 10 upon 25. So K effective is 2.5. Okay. 1 upon K effective is 1 upon 5 plus 1 upon 5. So it is 10 upon 25. So it is 2.5. So X is F upon K. So it is 40 meters. Okay. So the minus in that formula was given as given for restoring force. So when F you write F is minus kx, F is there is restoring force. However, you can uh, now why it is minus 40? Can you tell me the spring the length of the basically we are asking change in length. So it it is 40. Mm,
Sir, F is equal to minus kx, no, sir, because we are expanding it, so that's why I have applied minus there.
actually that F is equal to minus kx. No, it is F basically first of all like here we are finding change in length. Okay, so and second, okay, so forgot that that F whenever you are telling F is minus kx, F is equal to minus kx, I told you right. I told you here, right? This thing, like this F is proportional to minus X is basically F is restoring force here. Okay, so let's say you have a spring connected here. If you apply force F in this direction, the spring will like from Newton's third law, right? If we apply some force F in this case, spring there will be restoring force in this. Uh, so first of all, let's say initially this was the length of the spring. This let's say this was equal to L. This was the length of the spring. So now there is change in length of the spring in this direction, but the that F in this F is proportional to minus kx is restoring force. So this F will act in opposite direction, whereas change in spring length of the spring is in this direction. Therefore, this F is proportional to minus s is basically in this case we are considering this restoring force. Okay, then only this minus sign will work. However, now whatever case we have considered, we don't consider this minus sign because we simply use formula F equal to kx, where F is the our force applied by us and x is change in length. So therefore you can simply put F as a positive, whatever value was the given, and it will remain positive only at the end.
Okay, sir.
Okay, if they mostly in most of the question you will find they won't consider this sign, but if they consider the sign, then you read it properly, like whether they have given force applied or restoring force, and then you decide the sign of the change in length or x. Okay, now let's say you have a spring of stiffness k. Okay, and if you cut it equally, so let's say initial length was L, and you are cutting this spring equally into L by 2 and L by 2, then the stiffness of this half spring will become 2k. Okay, and similarly if you have again you consider a spring, and You cut this spring like, let's say the x is the length in one side and x or y is the length on the other side, and total length, initial length was x plus y. So in this case, the basically spring constant of this side of the spring will be k into x plus y upon x, and in this case it will be k into, let's say k was the initial one, k into x plus y upon y. So like if you have a spring of some sorry, not spring constant k, and if you cut it into smaller pieces, so means it, as small as you make it, it is spring constant will increase, because like let's say if you have a same spring you consider, if it is longer in length, then it will be easier to compress. Okay, it will be easier to compress. Easier to compress means basically, since f is equal to kx, if you apply some force, it the compression will be more, because let's, okay, okay, I will explain it. So let's say you have a spring, uh, it is having initial length L and spring constant, let's say K. So in this case, F is equal to Kx. So you need to apply force F to compress it uh, by length X. Okay. However, if you cut down the spring into half, so its length now became L by 2. So if it become L by 2, we know that this spring constant will become 2K. So in this case, if you have to compress it to again by X, then you will have to apply force equal to 2F. Okay, because this force, this spring constant became 2K. So you need to apply force 2F to compress it by same length. So therefore, when you make the spring shorter, or if you cut down the spring, its spring constant or its stiffness increases, and the way it increases is given as, let's say this is the initial spring, you cut it down like this, where this length is become x, this length is y, and total length, initial length was x plus y, and let's say initial rate constant was k, then rate constant of this side of spring will become k into x plus y by x, and the rate constant for this side of, sorry, not rate constant, spring constant for this side of spring will be k into x plus y upon y. Okay, so let's say we have a spring with spring constant k, and we uh, cut it in a way like, initial, let's say initial length was L. So now the length of this section is 2L upon 3. Length of this section is L upon 3. So the spring constant for this section will become k into total length L divided by 2L by 3. So it will become, L will get cancelled, 3K by 2. Similarly, spring constant for this section will become K into total length L divided by length of, now like present length. So it is L by 3. So LL will get cancelled. It will become 3K. Similarly, if you have a spring, you it is having initial length, let's say L, and initial spring constant as K. Now you cut it down in a way that this section become 2 by 5 or 3 by 5 L, and this section become 2 by 5 L. Then spring constant for after cutting, spring constant of this section after cutting will be K into total length divided by present length, that is 3 by 5 L. L will get cancelled, it will become 5 by 3 K. Similarly, spring constant for this section will become k into present initial length L divided by present length 2 by 5 L. So L will get cancelled. It will become 5k by. So now let's see one question. Spring having spring constant k, spring having spring constant k is cut into half. Okay, so they have given a spring. Let's say it was having length L, spring constant k. Now they have cut it down so into half. So now the new length is L by 2. Okay, so we know that its spring constant will become k into initial length upon present length. So LL will get cancelled. It will become 2k. Okay, the two springs are connected in. So similarly, for since it is half, both are half, we got two springs of both with spring constant 2k. Okay, now the two springs are connected in. The two springs are connected in parallel with each other. What will be the new value of spring constant of combination of spring? So what will be new or k effective, final k effective? So now if you connect them in parallel to some object, both are having spring constant 2k. So k effective will become 2k plus 2k. So it will become 4k. Got it? Understood? Okay, fine. We'll take some 15 minutes break. We will meet at 6:35. So we'll see one difference in spring and normal string or cable problem. So you can see the screen, right? Okay. So let's say we have a two different masses. Let's say one is 10 kg, other is 20 kg. So we know that when we have connected it using cable or a string, there will be different tensions in two different strings. And in let's say you consider a case where you cut down this, you have cut down this string from here. So in this case, this will both will be subjected to acceleration due to gravity g. Okay. However, this is not the case with springs. Okay. In this case, if you cut this down, the both will move with acceleration due to gravity, that is g. However, let's say now you have springs. In similar case, you will consider using spring. Let's say this is 20 kg, this is 10 kg. So you know that now if g is, let's say, 10 meter per second square, then restoration force or force basically or tension in this string is basically 200 Newton. Tension in this spring will be 200 Newton, and in this spring it will be 300 Newton. So now if you consider the case, okay, if you consider the ability of this, so there is a force acting, let's say this is T or this is F, which is equal to 200 Newton, and there is a weight acting downwards, that is 200 Newton. So if now in this case, if you cut it down, like if you cut this spring here, so or let's say if you cut this spring here, okay, at this point, if you cut the spring, so this 20 kg mass will move with acceleration due to gravity g, downwards with acceleration due to gravity, okay, g only. Whereas this, if you consider this 10 kg mass now, okay, so before cutting this spring, this 10 kg mass, it was subjected to this tension in this string T2, spring T2. Its weight was acting downward. Let's say it was mg, and there was a tension in first spring, that was T1. However, and it was in complete balance. Okay, it was in equilibrium, or it was not moving in any direction. Okay, it was stable. So if you cut it down, this T1 will vanish. So this T1 will vanish, means basically net force T1 will act in downward direction. So in this case, the acceleration, this basically this body will get acceleration which will be equal to T1. That is its uh, that was the tension in the string which we have cut, and divide by its mass. So this will be the acceleration of this body if this spring you cut it down, and it will not be equal to acceleration due to gravity g. Okay, so similarly, now if you consider this spring again, let's say this mass is m, this mass is also m. Okay, so in this case, if you consider this bottom body or bottom mass, of course its mass weight is acting downwards, that is mg. There is tension upward, let's say T1. So tension in this spring is basically mg. Okay, now if you cut it down from this location, so of course the tension in this string was 2 mg, mg plus mg. But if you cut it down from this position, earlier this, if you draw the FBD before cutting out the spring, this was mg, This was 2 mg, and its weight was acting downward, which was equal to mg. T1 was mg, weight was mg, and T2, let's say this is T2. T2 was 2 mg. But now if you cut this spring, this bottom spring, so this mg will vanish. So now this body will be under net force of 2 mg minus mg is mg in upward direction. So therefore, the acceleration will be F upon ma. So mg, sorry, acceleration is F upon m. So mg upon m will be the acceleration in upward direction. Okay. If you cut it down, if you miss at the moment you cut it down this spring, this will be the acceleration. This will be g, but in upward direction. Have you understood how it works? Okay, fine. I will explain it again. No problem. Okay. So if you consider this case, let's say this is tension in this string is T1, tension in this string is T2, and G is acceleration due to gravity. So therefore, you can find out, let's say if you consider the FBD of this mass, then mg will act downward, T2 will act upward, and T2 will be equal to mg. And if you consider FBD of this mass, then T2 equal to mg will act downward, its weight equal to mg will act downward, and T1 will act upward. So you will get T1 is equal to 2 mg. So in this case, this T is basically tension in this string, okay? And there is no restoring force as of spring. Spring has restoring force, okay, in it. So now, so like if you cut this string from here, it will simply fall down. Both will be under the acceleration due to gravity g. Okay, is this clear? Like, mm, for strings or cables, it is like if you cut any of the string or cable, it will that object will be under acceleration due to gravity, and there won't be any other force which will means at that moment it will be under acceleration due to gravity. Okay. Okay. Now, now let's say T1 is the or let's say T1 is the tension in this spring, T2 is tension in this spring, it is mg, and it will be therefore it will be equal to mg. It is similar in similar manner you can find it out, okay. But since it is a spring, even though there is a tension acting, uh, tension is acting like, let's say basically you are pulling the string, okay. Let's say tension is acting in this direction, uh, if you are pulling the string T1, then there is a restoring force acting in opposite direction, which is equal to T1 only. Okay. So this was okay. So it will try. So spring will try to come to its uh, initial position or previous. Okay, its initial position, you can say. Now, now if you consider the free body diagram of this, let's say this mass m. So it is not moving any direction. So basically, mg is acting downwards, T2 is acting in this direction on this mass. This is basically T2 and it is equal to mg. So both are balancing each other at a movement. Okay. Similarly, if you consider the free body diagram of this mass, there is a force 2 mg acting in upward direction. Then T1 is acting in downward direction, which is equal to mg, and its weight is also acting in downward direction. Now, if you cut this string from here, okay, if you cut it from here, T2 will vanish. T2 will become equal to 0. So this body will be under acceleration due to gravity g. Okay. Is it clear, this last point? If you cut this spring, so at the moment you cut this spring from here, this T2 or this mass will be under acceleration due to gravity. And let's say now you cut basically, if you cut it from here, the tension in this string T2 will become 0. So this, sorry, okay, this was T2. So now you consider, if you consider the FBD of this second body, okay, if you consider the FBD of this second body, since T2 has become equal to 0, so net force will be 2 mg is acting upward, mg is acting downward. So net force of mg will act in upward direction. At the moment you cut this spring, you got this. At the moment you cut the spring, the net force mg will act in upward direction. And therefore, you know that force is equal to ma. Force is mg here, which is acting upward, equal to ma. So will get cancelled. So acceleration will be equal to g, and it will act in upward direction. Okay. As soon as you cut down the spring, there will be acceleration g, which will act in upward direction on this mass. Is it clear now? Okay. So we'll see one question on this concept. Two blocks A and B of masses 3m and m respectively are connected by a massless and inextensible. Okay, sorry. Respectively, are connected by a massless and inextensible string. The whole system is suspended by a massless spring. As shown in figure. The magnitude and acceleration of A and B immediately after string is cut are respectively. So basically, okay. So, so mass A and B. So this is A, this is B. A is 3m, B is m. They are connected by a string, and the whole system is connected by a spring. Okay. So at the end, we cut this string from here. So what are the acceleration of A and B? We have to find out acceleration of the A and B immediately after string is cut. So if you draw the FBD, you will find out this tension in this part will be mg. Okay. And tension in this part will be m plus 3m is 4m. So it will be 4 mg. In spring, it will be 4 mg. In string, it will be mg. Okay. So now if we draw the free body diagram of this mass A, now there is this tension mg, there is weight mg of, sorry, weight 3 mg, and there is tension of spring that is 4 mg acting upwards, and it is in equilibrium. Okay. Similarly, if you draw the free body diagram of this mass B, so this is 3m, let's see, this is A, okay, this is B. So in this case, mass is mg acting downwards, tension mg acting upwards. So as soon as you cut this string, so this mg will become equal to, or this tension, so this T will become equal to 0. Here also T will become equal to 0. Okay. So as soon as this T equal to 0, so body B will come under acceleration due to gravity, and it will start moving downward. So therefore its acceleration will be equal to G, that is acceleration due to gravity. Whereas if you see this body A, the net force acting on body A will be, now this T has become 0. So now it will be 3 mg, 4 mg minus 3 mg. So net force will be mg And we know that F equal to ma. So A is F upon m. So here A is basically F, F is mg, net force is mg, and m mass is m, so it will be g. Okay, sorry, mass is 3m here, 3m. So mg upon 3m, so it will become g upon 3. So acceleration of body A is g upon 3. Acceleration of body B is g. Okay, this one is upward direction, this one in downward direction. Is it clear? Okay. So there is last concept of variable mass in this Newton's law chapter. Of course, all chapters are connected, but like variable mass. Let's see concept of variable mass. Okay. So what is meaning of variable mass? So what we have seen is force is equal to rate of change of momentum, that is dp upon dt. So this was the Newton's second law, and momentum is given as p is equal to mv. So d upon dt, force is basically d upon dt of mv, and therefore it will become equal to v dm upon dt plus m dv by dt. So till now we used to consider m dm upon dt equals to 0 because mass was constant. But if mass is not constant, then force will be equal to v dm by dt plus m dv by dt. Okay, so this will be the concept of force. Now, mm, okay, so let's consider one example on this. So sand is being dropped on conveyor belt. Sand is conveyor belt at at a rate of capital M kg per second. The force necessary to keep the belt moving with a constant velocity of v will be. So find force necessary to keep the belt moving, to keep the belt moving with a constant velocity of v with a constant velocity of v meter per second. Okay. So of course, in this case, we will have to use this formula where mass is also changing. Like mass is basically sand is being dropped on a conveyor belt at the rate of m kg per second. Okay. So we are increasing the mass of sand that is coming onto the conveyor belt. So therefore, we cannot simply assume that mass is constant in this case. So we know that F is equal to rate of change of momentum. So momentum is P is equal to mass into velocity. So this will become d upon dt of mv. So if you differentiate this, you will get v outside dm upon dt plus m outside dv upon dt. So this is the force, basically this will be the force required to keep moving that conveyor belt. So however, in this case, they have given velocity is constant. Velocity is constant. So derivative of constant is basically 0. So dv by dt term will become 0. So therefore force required, so this term will be gone. So force required will be equal to F is equal to V dm by dt. So dm by dt is basically change in mass per unit time. So it is given as capital M in this question. So therefore force will be equal to velocity into capital M. So this much force will be required for keep moving that conveyor belt. Is it clear? So we will stop for 5 minutes, and then we'll start with the concept of friction. Okay. So now we'll start with friction. Okay. So friction is basically it is a force that opposes the relative motion. Okay, between relative motion between any two bodies. Okay. So friction is a force that opposes relative motion between bodies or objects. Is a force that opposes relative motion. So let's say, okay, so let's say we have a earth, means ground, and there is some object is moving with some velocity v. So friction is the force that will try to oppose this, or let's say it is moving with not a velocity, let's say it is moving with let's say some acceleration a. So friction is a force that will try to resist this motion. Okay, it will act in opposite direction of the motion of this body on this body. So and it will try to stop it, or it will basically try to resist the relative motion between the ground and this body. Okay, so in this case, if you consider on this body, let's say there is acceleration a, maybe some force is acting f, then in on this body friction will act in opposite direction to the direction of motion, let's say fr. Okay, now if you consider the two bodies, let's say this is body a, it is moving with velocity 1 meter per second, and there is body b, this body is moving with velocity 5 meter per second. So in this case, for on body b, friction will act in opposite direction. Okay, this friction. So the body B is moving in this direction, whereas friction will try to resist its motion, frictional force. Okay. Whereas if you consider the body A, so on body A, even though it is moving in this 1 meter per second, is both are moving in the right direction. On body A, the friction will act in this direction, because if you consider the relative velocity of body A, it is, if with respect to body B, then it is 4 meter per second in backward direction. Okay, relative velocity. And therefore on body A, force will act in this direction. Frictional force will act in direction of motion. So what it tells is friction basically resists as well as, or basically opposes as well as helps the motion. Okay, so in this case, since A was moving slowly and it was in contact with B, which is moving at faster speed, so therefore friction in between A and B is helping A to move at faster speed. Okay, whereas in case of ground, if you see like a object, like if you see there is a ground, one object is there, it is moving with c velocity v meter per second, then of course in this case the friction will oppose the motion, and therefore friction both help as well as oppose the motion. Okay, but frictional force always act in the opposite direction of relative motion, that you should be aware. Okay, so here, if you consider relative motion between B and A, so B was moving at 4 meter per second in towards right with respect to relative to A. Therefore, friction was acting in opposite direction. Okay, on this on B. Whereas if you see A is moving at 4 meter per second towards left with relative to B, and therefore friction was acting opposite to the relative motion. So this is how it works. Okay, is it clear till now? Okay, so friction is basically proportional to the normal force. Okay, so let's say there is a ground and there is a object of 10 kg. So if there is object of 10 kg, of course there will be normal reaction of mg acting upwards. Okay, and here, so here in this case it will be 10 is m, g is let's say 10, it will be 100 newton. So normal force is 100 newton. Whereas on same surface, if there is object of 5 kg, then the normal reaction will be 50 newton. So if you start pushing this object, both the object, so you will face the friction in this case, first case, let's say this is first case, this is a second case. So friction in first case will be higher than that of second case, because friction is directly proportional to normal reaction, and in first case the normal reaction is more compared to that of second case. Okay, and let's say this is FFR, this is frictional force, is directly proportional to normal force. Okay, and therefore FFR, that is frictional force, is given as mu into N. Okay, now this mu is coefficient of friction, coefficient of friction. Now you know that the unit of friction force, it is a force basically. Unit is Newton. Uh, Force of normal reaction, which is also a force is also Newton, and therefore this Newton gets cancelled, and this uh, coefficient of friction mu is basically unitless quantity. Okay, it is a unitless quantity and it do not have any unit. Now let's see the types of friction. Okay, so first one is, let's say, mm, or maybe before moving to the types of friction, let's see one example. So we have one object. It is having mass 10 kg and acceleration due to gravity, let's say it is 10 meter per second square. So therefore, normal reaction acting in upward direction is 100 Newton. Coefficient of friction, let's say it is 0.1. So we know that frictional force, let's say we have applied force of 10 Newton on this body in right direction. Mm, or let's say the coefficient of friction is, let's say, zero point 0.2. Okay. So frictional force will be 0.2 into 100, that will be equal to 20 Newton. So basically this is the maximum frictional force that can act on this body, okay, and it is fixed. So it is known as limiting friction, okay. This is, so coefficient of friction is zero point 0.2 and 100 is the normal reaction. So FFR is 20 Newton. So this is basically limiting friction. So this is the maximum frictional force that can act on a body. But since in this case we have applied force of 10 Newton, this 10 Newton is not enough to break the friction. So, therefore this body will not move, and the frictional force in this case will also be equal to 10 Newton. Okay, equal and opposite. That is from Newton's law. So basically 10 Newton you are applying, but since it is not crossing the limiting friction, so that is the minimum force required is 20 Newton. So so now if you consider the same case, let's say, now if you consider 10 kg mass, for 10 kg you know that normal reaction is 100 Newton, and let's say if you apply 15 Newton in this case. So again 15 Newton is less than the limiting friction value, and therefore in this case also this object will not move, and frictional force acting in this case will be equal to force applied, that is 15 Newton. So this value of frictional force, let's say in this case it was 10 Newton, in this case it was 15 Newton. This is known as basically static friction. So static friction, because the object is not moving, still there is frictional force on the object because of the applied force. Okay. Since you have applied this 10 Newton force, there is friction of 10 Newton, but the object is not moving, and therefore it is known as static friction. And it will start moving only when you will cross the limiting frictional force value, that is 20 Newton. Okay. So now let's say, also you can, like, even if you reach, if you apply 20 Newton force, then also the frictional force will become 20 Newton, that is static frictional will reach the limiting value, that is 20 Newton, but since the object is not moving, it is still a static friction. However, let's say now you have applied a force of 50 Newton, and let's say this mass was 10. So mm, since coefficient of friction is mu is 0.2, F limiting is basically 20 Newton, you know that. So therefore, in this case, the 20 Newton frictional force will act in opposite direction to the applied force. So net force acting on this 10 kg mass will become 50 minus 20, that is equal to 30 Newton. And therefore acceleration of this object will be F upon m, that will be 30 by 10 equal to 3 meter per second square. And in this case, the frictional force acting on this object will be known as dynamic or kinetic friction, because in this case the object is moving with acceleration of 3 meter per second square. So therefore it is known as dynamic or kinetic friction. In first case it was not moving, and therefore it was known as static friction. And limiting frictional force is basically the force above which the body will start moving. Okay, so this is how you can and learn about the type of friction. Is it clear? So if you draw the graph of, let's say, this is uh, frictional force, and this is applied force. Okay, so we have seen when we applied 10 Newton force, the frictional force was also 10 Newton. Okay, and limiting value was 20 Newton. So when it was 15, when applied force was 15, frictional force was also 15. When applied force was 20, the frictional force was also 20. Okay, so till the point the frictional force reaches the limit force. So let's say in this case, what we have seen, if this was 20 Newton applied force, then the frictional force acting was also 20 Newton. And before that, let's say if it was applied force was 5 Newton, then frictional force was also 5 Newton. It was increasing proportionally. But after it reaches this limiting value of 20 Newton applied force, then no matter how much you increase the applied force, frictional force will remain constant. So even if you apply 1000 Newton or 10,000 Newton force, then also this value of frictional force will remain constant. So till this point it was not moving. So this point is basically was limiting frictional force. And since after this point it starts moving, this is basically known as dynamic or kinetic frictional force. And before, from this origin point to this point, it was static frictional force. Okay, so I just wanted to tell you one thing. So we have seen this graph. Okay, in many problems they just mention mu as coefficient of friction, mu or mu s or anything, mu mu s as coefficient of friction. So if it is the case, so in this case, the frictional force FFR, limiting frictional force, will be mu into normal reaction. So it will be like, it will go like this and then it will remain constant the way we have seen above. However, in actual case, means in actual scenario, this mu or mu, it is basically known as static, let's say static frictional coefficient. Okay, and there is mu k or mu d, that is dynamic frictional coefficient. So in reality, what happens is this static frictional coefficient is always greater than the dynamic or kinetic frictional coefficient. Okay, in actual case. So now if you consider the graph again, so let's say in this case you have static friction coefficient maybe as zero point 0.2. Okay, and there is a object of mass 10 kg. So normal reaction is 100 Newton. So let's say you applied force. So 100 mu n means 20 Newton is the limiting frictional force. So until 20 Newton, whatever force you apply, that will be the your friction equal to frictional force. Okay, both will be equal. Frictional force, let's say this is applied force. So until this point, this is basically known as static frictional force. And let's say you have dynamic frictional coefficient as, let's say, 0.18. So as soon as the object will start moving, as soon as you cross 20 Newton force value, then it started moving, and then this frictional force value will come down to 18 Newton. Okay, no matter, this is 20, no matter how much you change the applied force. Okay, but in our syllabus, means whatever I have seen, mostly they do not give two different coefficient. So there is no need to worry about this. They just give single coefficient, like uh, coefficient of friction only. So you can just consider this as the static friction, this as the dynamic friction, and dynamic friction value will be equal to limiting friction value, and static friction value will depend on applied force. If it is 5 Newton, they apply until the object is not moving, it will be equal to applied force. If applied force is 5 Newton, static friction will be 5 Newton. If applied force is 10 Newton, static friction will be 10 Newton. Is it clear?
Sir, if
Yes.
uh, if applied force is same as that of frictional force, then the object will move or it will be in stationary position, sir.
It will be in stationary. Means if it is in limiting, if it is equal to limiting frictional force, then it will be in stationary position. It will not move. Net force will be zero, so it will not move.
Okay, sir.
Okay. So if someone tells, uh, calculate static and limiting frictional force for a given case. Okay, so let's say you have one object of mass 10 kg. Coefficient of friction is given as zero point 0.1 and 2 Newton force is applied on this object. So find out the static and limiting frictional force. So first, our first task will be to find out the limiting frictional force. So if 10 kg is the object, is the mass of the object, then the normal reaction provided will be equal to mg, that is 10 into 10, that will be equal to 100 Newton. So normal reaction is 100 Newton, and limiting frictional force will be basically equal to mu n. So it will be 0 0.1 into 100. So it will become 10 newtons. Okay. So limiting frictional force is 10 Newton. So until you cross 10 Newton value, the object will not move. Okay. So therefore, if you are applying 2 Newton force, of course, there will be static frictional force of 2 Newton, which will act in opposite direction to the applied force. So this is how you have to solve the questions. So, and now let's say find out acceleration of object in given case. So again, let's see, you have 10 kg of mass, you have applied 100 Newton force, and coefficient of friction is 0 0.1. So in this case also, normal reaction, since weight of 100 Newton is acting downwards, normal reaction of 100 Newton will act upwards. So limiting friction will be equal to mu n into n, that will be 0.1 into 100. So that will be 10 Newton. So since you have crossed 10 Newton, so 10 Newton force, frictional force will act in opposite direction. So net force acting will be equal to 100 minus 10, that is 90 Newton. And now if you put it equal to m into acceleration, so 90 will be equal to m is 10 into acceleration a, so acceleration will be 9 meter per second square. Okay, so let's take one more example, then we will stop. So a block of mass 10 kg placed on a rough horizontal surface having coefficient of friction mu is equal to 0 0.5. If a horizontal force of if a horizontal force of 100 Newton acting on it, then the acceleration of block will be. So option A is 10 meter per second square. Option B is 5 meter per second square. Option C is 15 meter per second square. And option D is 0.5 meter per second square. So a block of mass m 10 kg is placed on rough horizontal surface having coefficient of friction 0.5. So let's say this is a surface and mass of the block is 10 kg. Coefficient of friction is 0.5 and acceleration due to gravity is, let's say, 10. Okay, g is equal to 10. So in this case, of course, the normal reaction of 100 Newton will act in upward direction. So limiting frictional force will be zero point 0.5 into 100. That will be 50 Newton. So is the limiting frictional force. Now 100 Newton of force is acting on the block. So of course it is more than limiting frictional force, which is 50 Newton. So net force acting on the block will be 100 minus 50, that is 50 Newton. That is the net force acting right on the right in the right direction. So F equal to ma. So 50 is equal to 10 into A. So A will become 5 meter per second square. You got this?